And let's think about a force that was pointing in the x direction, or the 1 direction, right? Sigma x, and it was acting on the y face, then it would be sigma x y, right? And that would be, for the little element that we might draw, if this is x and this is y, that would be this couple. Now if you have that couple, this should spin, this would accelerate rotationally, right? And remember, this is the area here. So we need to have this couple in order to get this thing to be stationary, in order to be static, right? And that couple, right, is going to be sigma y x. Force in the y direction on the face perpendicular to x. Okay, so let's look at a Mathcad worksheet, and we'll even go further in this. We know that MPa can be defined as PA times 10 to the 6th. Versions of Mathcad that are further along, I think 13 and above, MPa is an automatically defined function. But if you're not using the case, this makes sure that you have. You can, of course, can always check by typing in MPa and putting a regular equal sign. Okay, so I've defined a matrix of stresses here. I defined it by defining a sigma. This sigma was entered by entering an S. Then I hit Control G. Right? Then I hit colon. And then I went to the menu and pulled down the matrix symbol. And I filled in these numbers in each of the little placeholders that would come here for the 3x3 matrix. And then I wrote times MPa. Okay? Then if I want to pull out the terms, and you notice here, origin is equal to 1 is already defined. If I want to pull out a term, I type sigma, left bracket, 1 comma 1, and an equal sign, and it pulls out that term. If I want to display it as MPa, I'd have to go to the end where there's a little placeholder box and type MPa in it. That's what I did here. Okay? If I want sigma 2, 3, right? So this was sigma, S Control G, 2 comma 3 equals 40. I filled the placeholder box and it gave me 40 MPa. It was pulling, right, from the second row, third column. Remember, this one is 1, 1, this one is 1, 2, this one's 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3. Okay? Now, we're going to think about these stresses as being applied to a box-shaped part with sides 5 millimeters, 6 millimeters, or 11 millimeters, and we want to find the forces required. Kind of a bogus problem, but at least shows the concept. Right? This is an inelegant means ugly, solution. So we can define this stress as F of sigma comma A is equal to sigma times A. A little bit simple. So if I take F of sigma 1 comma 1, remember all that other prior work in slide 4 is above this, sigma 1 comma 1, that pulls out that stress and sticks it right here. Then I put in the area of that face, right? That is the area of the face, right? The one face. Okay, and I get, this is the result, I get my force in newtons. And this way I can get my force in, at least from that, the component of force that comes about from these stresses, right? I get each of these components of force, and this is going to be the F of x, or F sub 1, F sub 2, or F sub y, and the F sub 3, or F sub z. That's what I get for each of these results. Okay? Not a fancy solution. A more elegant solution defines each of the areas. So A left bracket 1, A left bracket 2, and A left bracket 3. And then if I enter, you notice I can enter each of these, and then if I type A an equal sign, it automatically gives me my column. Right? So it knows, if I've given those three terms, that A is defined by those three terms. Okay, pretty cool. and then I put it, in this case, it's generating it into meters squared. Obviously, it'd be nicer if it was millimeters squared, but you can always enter that in the little placeholder box that's available. So if we go and we continue further, once again looking at this function, we can take sigma f of sigma comma a, and then if we get the results, remembering that here it doesn't remember, it only takes the terms from above, so it goes to the sigma that's way above up on slide 4, and the a that's defined right here, and it generates those same stresses that we saw earlier. That's a prettier solution. We can look at a little bit more complex problem. Here there's a little bit more complex stress state. We only have zeros in a couple places, right? Using the same areas, so now that I've already defined the areas, I can pull out each of those forces. Okay, so let's keep cruising forward here. Let's look at a few of these stresses. This is sigma 1, 3. You'll notice it's pointing in the x direction on the face perpendicular to 3. This says minus sigma 1, 3. The question is, which one of these is right? Right? Is this the negative of sigma 1, 3? Or is this sigma 1, 3? Well, this, right, this should be acting up here. Right? This is a couple, right? So something has to be changed to make this right. So this arrow would be a positive, so this must be negative, so this one also must be negative. Okay, so we need to have both of these be, so this is the opposite of a sigma 1, 3, so it's a negative value, and this is also the opposite because it's pointing in the positive direction on the negative face, and the couple means they have to be the same. Okay, this is another problem with sign conventions. If I define this as minus, it gets confusing in terms of the magnitude, but it's important to note that sigma 1, 3 is defined as positive, and sigma 1, 3 defined as positive would be a couple with that arrow and with this arrow operating on the cube. Okay, so this is the opposite of that. These two, let's see if they're right. Right? This points in the negative z direction on the positive y face. So that is the opposite of sigma 3, 2. Sigma 3, 2 operates like this. Okay? Let's look at a few others. You can take a look at this on your own. I've only shown a couple of them just to see. You can check on your own to see if these are right. So these are the two I already did. Right? You can check on your own and decide what's going on with these two.